what I want to do in the next 45 minutes is give you a framework in which to think about segmentation so that when you read new papers, you can sort of very easily figure out which of the pieces of the common methodologies they're using, as well as when they're innovating, in what particular aspect of it they're innovating. And then in the next 45 minutes, Raman will take over and give you much more specific details about certain aspects of segmentation. Okay, so let's get going. So in general, the problem of segmentation, I hope I don't have to define for many of you. The idea is that you have an image and you're looking for an object here. Can everybody see this clearly? Should I draw bigger? Let's try this. Would this work? You're looking for something like this. Is this acceptable sort of for size? Everybody sees an object in this scale? I just want to calibrate it for the first one. So we're looking for an object in the image. And the question is, where is the object? And in particular, when we talk about segmentation in the contrast to localization, say, or classification, we would want to know detailed description of where it is. So just to say that it's in the center is not good enough. We're going to want to know to the detail of the pixel in the image where the boundary of the object is. Okay? So in order to describe that, you need three components, and we sort of will talk about each one of the three components. First is representation. So the representation of the object, is this font good enough? Should I write bigger? No? This is good? Okay, great. So first, you need to figure out how to represent the object. And in all of the computer vision / medical image work in segmentation, people have converged to basically two fundamental approaches to representation. One of them is, I will call it boundary-based. And it is that if you have a boundary in the object, I'm going to put little dots, points, along the boundary, and I'll model XYZ or XYZ in this part of the world, location of that point. And that effectively represents the object as a mesh, because I'll oftentimes also record which point comes after which point and which points are neighboring each points in 3D, right? So effectively, we're approximating the object by a set of points and lines connecting them. And you can get arbitrarily fancy about this, and I'll talk about it just briefly later, but for practical purposes, it's useful to think of it as boundary points. A variant on that is actually representing the object through its medial axes. So for example, and so for those of you who have never heard the term, think of it as the center line of the object, right? So here, I might think of my axis as like this, and again, it will be points. And the reason why I clumped this also into boundary representation, because every point tells me what radius of the circle to draw so that it touches the boundary. And so every point will be characterized by its location and the radius of the point. And again, I think of that as boundary-based representation because the optimization will be on objects like points in space with the neighboring information. Okay? So this is one representation, and the second representation is called voxel-wise or volumetric representation. And the idea is that we're going to start with the grid of voxels that are already given in the image. And in every voxel, I'll say whether it's inside or outside. So I'm going to say that this guy is inside, and this guy is inside, and this guy is inside, but everything else is outside. And so you could say this is actually sort of a little bit of an approximation of the object I actually want to represent that looks like that, right? And so some of the voxels here, you can see, are called partial voxels or partial volume voxels. And I'm drawing everything in 2D, and I count on your imagination for the third dimension. And so this is a bit of an approximation of that. As I said, it's either voxel-based or volumetric. And this approximation, the fact that you're not capturing the boundary precisely, but it's sort of, oftentimes people talk about this as being terraced representation, is well worth it in computation. In the sense that many methods exist that run very efficiently on representations like this, but have troubles with representations like that. So here you can get very, very close to the true boundary in terms of representation, but there are computational issues that come up when you actually try to approximate, when you try to estimate this from the image. And I'll talk about them in a second. Okay, so this is our representation. And there will be 2 representations, and I'll talk about how people deal with each one of them with respect to other components of your recipe. So that's the first ingredient for segmentation recipe. The second ingredient is quality measure. So quality measure is a function that takes an image that you have, a segmentation that you created. So that could be either actually tessellated voxel representation that I just talked about, or a curve that tells you what the object is. However you choose to represent it, given a particular image and that representation, the quality measure tells you just one number. So it maps 2 things, 2 objects into a number in R, and it tells you how good the segmentation is of this object, okay? And so this sounds very abstract. We'll make it concrete in a second. But let's just talk about where this could come from. So you could have some ideas about what your object looks like. For example, if you're looking for a bright object on a dark background, you might want to collect voxels outside and measure how dark they are, collect voxels on the inside and measure how bright they are using your knowledge about domain problem and spit out a number that is a agglomerate number summarizing that. You might have an intuition that your object has to be sort of clumpy and contiguous. So you might want to create a measure that tells me how clumpy and contiguous this object is, and penalize objects that have, penalize segmentations that also have spindly things here that are disconnected. Okay, so if you penalize them, so we'll talk in a second how measure of quality, sort of, it seems like you would want to maximize it. It seems that computer vision in general is a very pessimistic field going after physics. So the way they think about this is always not measure of quality, but the penalty on your problematic problems, and you're going to minimize the cost function or minimize the penalty, okay? And so I'll use both terms back and forth, and I'll make it clear whether we're maximizing or minimizing. Every time you talk about the energy, you want to minimize that. And so like I think of that as a little bit of a, or you want to maximize the reward, like those ice creams we've been getting for coffee breaks. So, okay, so you have the quality measure. The other thing you could do for quality measure, and I'll make it specific, is say, I've seen these objects before. I'm going to learn something about these objects, and then I'm going to measure how your segmentation, whether your segmentation is similar to the objects I've seen before of this sort. And I'm going to penalize you if this segmentation looks nothing like what I've seen before. So these are called prior-based, model-based, atlas-based segmentation methods, okay? And so we'll instantiate those. So this quality of measure is not necessarily only how well the segmentation represents the image, explains the image that you've seen. It can also say something intrinsic about the segmentation itself, right? How smooth, contiguous, or like what you've seen it is. Okay, and so typically, this term splits into 2. And so this is, I'm giving you what we've thought about so far as a field. Please go away, remember this taxonomy, and do something different, because we're sort of tired of this taxonomy, but this is what it is now, okay? So everybody seems to be stuck with 2 terms. One of them will be called data term, or image term, and you can guess what this does, right? You usually shove into these terms all of the formulas that describe how well this segmentation explains this image. And then there is another term that has about 1,000 different names depending on what school of thought people come from. So it could be smoothness term, it could be prior term, which works for people who work on atlases or looking at your experiences. And it could be regularization. Every time you hear the word regularization, it basically says, I've built my representation, and I just try to use how well it explains the image, and I'm getting all these spindly things. So I'm going to regularize it, meaning add a term that reflects my intuition about how the representation has to be small, compact, something, so that the little spindly things go away. Like that's roughly what regularization stands for. Okay, so there are two terms. And then the third one, and these two terms, I should say, there are again two schools of thought. And so a lot of this is taxonomy, and then we'll actually make populated with interesting math. Okay, so there are two schools of thoughts, energy-based, which will say my energy is the energy of the image term plus the energy of regularization or smoothness or whatever you put here that tells you sort of what the segmentations, what good segmentations look like or prior. And so of course you want to minimize the energy because of all terms. So basically you want to minimize this over your parameters of the segmentation. And it's the energy of the image term and the energy of the regularization, okay? And so this is sort of energy-based thinking. And because you want to minimize energy, oftentimes these are called cost functions, and you minimize the penalties of the cost functions. This thinking is affected by how physicists think about an energy of a system that settles into minimal energy. The other approach is probabilistic approach. And it says that your probability of the segmentation is proportional oftentimes, but we won't worry about the coefficients. It is a probability of the image given the segmentation times the probability of the segmentation. So this is my segmentation, and so this is oftentimes referred to as likelihood of the image. And this is referred to the prior term on the segmentation. So if you take negative log of this expression, you end up with the sum of two terms. And so the probabilistic approach, you maximize the probability over the parameters. Okay? If you take negative log, you end up with the minimization of the sum. So oftentimes, when somebody stands there and says, hey, I'm doing the generative probabilistic modeling, the energy-based guys say, big deal. You just take the log of your function and you're back in the energy world. So actually, there are several papers in the field that show equivalence between these two approaches. If you're not going to estimate certain parameters of your prior, if your prior is fixed, these two approaches are equivalent. So you're either minimizing energy or maximizing probability. They're equivalent through the negative log transformation. Okay, so this is how we think of goodness measures, right? So the question is, how do you optimize it? So this is the third ingredient, optimization. Right? It's actually how do you search the space of parameters, and by parameters I mean description of your segmentation. So it could be pixel-wise representation, it could be by points. You can actually parameterize it. For example, take Fourier transform of the location of the points and optimize the Fourier coefficients. However you choose to represent your shape, you have to search for an optimal configuration that minimizes the energy or maximizes the probability. And this is what Ramin is going to talk about mostly. Okay, so I'm going to avoid this topic here with the exception of one little detail, which is that in the probability world, there is, and I'll touch on it just briefly, in the probability world, there is a special optimization technique called EM. Some of you might have heard about this, that takes advantage of the fact that these are valid probability distribution. So it's a very particular trick that is specific to probability. Every time you see EM, it's basically an optimization technique that allows you to maximize probability by taking advantage of the fact that both of these components are probabilities. Okay? And because of that, you get sort of additional advantage because you know the structure. In general, in everything that Ramin will talk about, the name of the game is you can't possibly enumerate all possible configurations of the parameters. So the more you know about the structure of the parameters that gives you good answers, the better your optimization is going to be. And so you'll see a bunch of examples of that. Okay, and so what I want to focus on in the remaining however many minutes I have, they'll tell me eventually, is the measure of goodness of the segmentation. Because basically that's where it's at. And most of the time when you're writing segmentation algorithms, which I've done a bunch with my students, what happens is you formulate your measure of goodness, you find a good optimizer, you make sure that the ground truth segmentation that the person would create gets a very good value under that. You also find the optimizers, and then you start getting answers, and the answers clearly don't make sense. And when you look at it, what happened was your optimizer found a way to satisfy your cost function and make it really small by making completely unreasonable guesses about what the segmentation is. And it all becomes about how to put more constraints on what it means to be good segmentation. Okay, and so this is what I'm gonna do. Okay, so the intensity term. The intensity term people seem to pretty much have consensus about, and it's the most boring term on the planet. But yet there are several ways to think about it as well. So the idea is that if I have a segmentation, you said this is not big enough. Here we go. If I have a segmentation, this is my proposed segmentation, and I haven't said yet even how I represent it, right? Whether it's a set of points or whether I actually labeled every voxel by 0 and 1. How do I evaluate how well it represents the underlying image? Effectively, almost everything you see in the literature, and so when you read the new paper, I challenge you to think of these terms and think about whether it fits or not, is I'm gonna go look inside and I'm gonna look outside and I'm gonna try to say something about how well these two cluster separately into two different clusters. Effectively, what it's going to do is, the model in my mind always when I read about intensity terms is that I roughly I'm looking for a segmentation that will create good separation between background and foreground or object, right? And so all of the disagreement in the field seems to be about what it means to characterize that, because you can still quantify this in many different ways. So one of the most famous ways is what's called Chan-Vesey. And you can look up the papers later. What it does is it takes the image, evaluates it at point X, subtracts the estimated mean of the intensity from the class, meaning object or background, of the location X, takes square of it, divides by the standard deviation or variance, right, of the same class. It sums over all pixels in the image. Okay, so another way to think about this is I'm going to go separately over pixels in the foreground and set pixels on the background, and I'll look at how little variation there is relative to the estimated means. And so many algorithms that rely on this iteratively estimate membership of the voxels, labels of the voxels, whether they're in background or foreground, and re-estimate the means and the variances, because the means and the variances depend on which voxel got assigned to which background or foreground label, right? Because to estimate them, you have to sum over those voxels. And so they alternate between estimating which voxels belong to the object and then estimating mu and sigma, computing this formula, and chugging along. And so each step tries to minimize this expression, okay? Another very common approach to this problem is what's called EM segmentors, and I don't want to talk about actually using the EM algorithm to estimate, but how they view intensity term, right? So the typical one is EM segmentor, and so this is Sandy Wells had the very first paper with this idea of using EM's algorithm to fit it, and then Koen van Lippert had, so let me write it here. Lippert had a beautiful paper in '99 actually that very cleanly laid out what it means with spatial priors. And so there is a reading group on Wednesday that if you're interested in taking that paper apart and putting it back together, that's what we're going to do there. So both of these papers are very widely cited. Those are sort of the seminal papers in the EM segmentation. Both do the same thing. And they're saying rather than sort of think about it this way, we're going to think about it as really clustering. Okay, so it will be product over every pixel, sum over two labels. Either you're inside or you're outside. Probability of the intensity that you get in that pixel under the model of that class. So under the model of that label times the probability of that label. And let me put X here, right? So it's a probability of in that particular voxel, okay? So so this looks very different from this, but let's decipher actually what it says. Suppose I make my probabilities binary. So the voxel is only allowed to be either in the foreground or in the background. I say the probability has to be either 0 or 1. Then the sum devolves into just one term, right? And typically, people assume Gaussian likelihood. So this is going to be e to the minus I minus mu divided by sigma 2 sigma squared, and this has to be squared, right? So it ends up being product of these guys. If I take log, what do I get? It's exactly the sum over all the pixels of the difference between the intensity in a pixel and its mean divided by standard deviation. So in fact, these two methods are equivalent in how they treat the intensity term. It's exactly the same representation, which is that given the class, the pixels are generated from a Gaussian distribution. And of course, the way I talk gives away immediately to you that I'm thinking about this in probabilistic terms rather than energy terms, but I really do think that they're completely equivalent. Okay, and so what happened here, so you could actually, this tells you how to change this to have assignments between 0 and 1 so that you can have some sort of confidence in your segmentation. So your pixel could be 0.75% one object and 0.25% in the background, for example, right? You'd have to augment it with these weights. Okay. So this is basically the only way people have thought about to do intensity modeling that transfers across different applications. It's entirely possible that there are applications in which people do something different, but I haven't seen anything else that survived several applications. Okay? So this is easy. Now let's do the prior regularization shape term. It turns out that here the details matter. And whether you work with the point-based method or boundary-based method that represents boundary by collection of points and voxel-based methods, things are different. And so I'm going to talk through both of them and be done. Okay, so I call it prior term. But you can call it regularization or anything else that tells you that this tells you just how good the segmentation is without you even looking at the image, right? Does it look reasonable? So here, I think that there are two terms here. One of them is smoothness that people started doing long time ago. And effectively, if you see smoothness terms, they all look like first derivatives, second derivatives, right? So I'm going to take differences between the points, and I'm going to penalize squares of either first derivatives or second derivatives. And so I'm talking about prior term boundary-based. Right? Smoothness is really written in terms of first derivatives. And sometimes when people want to get really fancy, they do second derivatives. So thin plate splines, for example, is a regularization that uses second derivatives. The trouble, so it's a great idea, and the trouble with it, and I'm sure you'll see with, when Raman talks about this, it's a bit challenging to actually write optimizers for this that are robust. And so oftentimes people come up with representations that convert this to volumetric. Some of you have heard of level sets. Effectively, what the level set technique does is it takes boundary-based representation and does all these operations in the volume rather than on the boundary. So as I said, there are technical sort of subtleties here, so it's harder to implement. And the second term that the second option you have is sort of really truly prior term, and so I call it from examples. Suppose I give you a bunch of examples, and I tell you what these segmentations look like or these objects look like, find me something like that in the image, right? The most common, overwhelmingly most common approach here is to run principal component analysis or any kind of generative modeling from these examples. So let's think about how that would work. I'm going to take coordinates of my points, and I'm going to stick them into a humongous vector that I'll call S. So if you have, for example, 1,000 points, it's 3,000 numbers because you need to represent X, Y, Z. And my model is that they're generated from a Gaussian distribution. So there is the mean. Then I have this big vector, big matrix of vectors that represent principal components or principal axis of a big Gaussian times a set of coefficients, right? And so I estimate these from my examples by taking the mean of the examples and estimating covariance matrix of the examples and taking eigenvectors of that covariance matrix. These are what's called eigenshapes. Eigenshapes. And this is distributed as Gaussian with zero mean and diagonal covariance. And so the idea is I have very high dimensional Gaussian that spits out coordinates of the points. My examples are representatives of that Gaussian. So in the training phase, I'm going to estimate mean and covariance. And then when I do segmentation, my penalty term will be how likely my coefficients. So I'm doing optimization not in the space of coordinates of the points, but in the space of these coefficients. Right? Given a set of coefficients, I can generate the shape. Given the shape, I can generate predicted image, evaluate its image term, but I'm going to run the optimization in this abstract space of coefficients here. And the prior term will become my Gaussian likelihood, which you can guess. So let's think about it in the energy term. What would you do in the energy kind of approach? Instead of putting probability on it, you would say that you'd penalize squares of the coefficients, right? Because that's what the Gaussian will do, divided by the variance in those coefficients in the training set. So if along some dimension my shapes change quite a bit, then I'm going to penalize that particular coefficient more or less depending on how much it changes in the training set. Okay? So that's what the boundary methods do. The most famous paper about this that you should all read is by Kutz and Taylor. And then there are about 5,000 citations and papers that use this approach. Okay, and so on to the volumetric. Prior with volumetric. Volumetric methods are fantastic for people who care about computation because they're easier to work with. So the first term is smoothness. And so it's very hard to put global things like smoothness into volumetric methods. So instead, people at some point did this little hand wave gesture and said, awesome. Thank you. This was my timer. So people did this little wave hand gesture and said, actually, smoothness, what do we mean by smoothness? Maybe what we mean by smoothness is really just that the things are clumpy. And so they kind of quickly replaced smooth boundary with clumpy object. And so typically, if you read papers on this, they involve Markov random fields. It's, for those of you who have never seen the term, it's like Markov chains. It's generalization of a Markov chain in 1D to multiple dimensions. And the terms you see in these kind of cost functions is penalties on the label of pixel X and pixel Y, or voxel X and Y, when X and Y are neighbors. Okay? And so suppose I'm in the energy world and I want to minimize. Okay? And X and Y are neighbors. If I want my object to be clumpy, right, how am I going to define this penalty? So I have a penalty for when they're equal and the penalty for when they're not. Okay? Which one should be bigger? So X and Y are neighbors, and I want the object to be clumpy. Do I penalize equal labels or unequal labels more? Okay, great. Those for you who would penalize labels that are equal more, raise your hand. Those of you who will penalize the unequal labels first. Those of you who are paralyzed by this decision and would never work on segmentation because of this, raise your hand. Okay, so let's think through it. If two pixels share the same label, is this a good situation or bad situation? If you want clumpy objects. Good. So you're going to penalize differences in labels here, right? So this kind of situation. So oftentimes these look like, I don't know, something like e to the power lx, ly. And I always have to think about this from scratch, whether there is a minus or not. That's why I wanted to tell you, I wanted to show you that it's not, it's always easy to get confused, right? So if they're equal, it's going to be 1. Sorry, I'm going to do that. Okay? Just again, as I said, I can't do this on the spot, right? If they're equal, and I don't want to say, oh, this is easy, here's what you do, because then you won't know that this is not easy to do it on the spot. Let's do it here. So if they're equal, then it's equal to 1. If they're not equal, it's equal to 0, right? So it's either e or 1. So I want a minus sign in front of it. And of course, if you want to dial this penalty, you also put some little alpha here, so that it's not exactly e and 1, these two terms, but you can arbitrarily make it, for example, 1001, right? If they're not equal, it's a penalty of e to the 1000, or it's a penalty of 1, and if it's not, then if they're equal, then this number becomes very small, and so the penalty is very little, okay? So all of the Markov random fields kind of regularizers do something like this. They put penalty on neighboring voxels. They sometimes, Nikos, do you think there should be plus? You mean like, well, this is a logical term. It evaluates to either 0 or 1. Sorry? With the Lx is equal to Ly. Nikos is an expert, so he'll fix it actually for us. It's okay. He says it's okay. You can write it in your notes and say Nikos said so. Okay. So, but you get the gist of it, right? Actually, what you do in your algorithm is you set up two different penalties. You penalize unequal labels more, and as a result, then the optimizer will find configurations where neighboring voxels tend to have equal labels, which means the objects will be clumpy. Actually, so there are too many references to list here, for real. I'll give you one that I like because it was, to my knowledge, so again, Koen van Limpot and Tina Kapoor has done something like this. They were the first applications to brain segmentation. Okay, so as far as I know, in Mackay, in medical image computing, this was the first application of this method. But the field goes back to like 70s and basically has been used in computer vision in the 80s and the 90s. It's a very rich field, right? So if you look for references in medical image computing, probably Van Limpot and Kapoor are the two I would look up and sort of look at their applications, okay? And so this is the idea of smoothness. And I should also say that Davy Geiger, he's at NYU, I think, really smart guy. So he actually has a cool paper in the roughly early 90s showing that minimal length constraint in the boundary-based representation is equivalent to this kind of penalty in the volumetric representation up to some fudge factor. And so there has been quite interesting theoretical work by showing what happens if you think you're working in volumetric representations. There is an underlying boundary representation and vice versa. And if you're imposing these penalties, what they mean in the equivalent, in sort of what equivalent constraint would be in the other representation. Okay, and now on to the sort of learning from examples, right, for volumetrics. Okay, so in learning from examples, you build probabilistic atlas is sort of the most common approach. For some reason, in this particular domain, the probabilists have dominated the field. Somehow, you see many more papers that cast it in a probabilistic term than in a probabilistic way than the energy-based way. And the way you do it, the simplest way to do it, you register all the images together. And so this is the first time I mentioned registration, and I'll come back to it in a second. So you register all the images together, and you average the segmentations. If you want to give a fancy name to it, you say, I'm building a probabilistic atlas. Right, so, and of course, if you think about what's happening is you're estimating average probability or average frequency of the label to the object in every voxel. Okay, and so once I have that atlas, I can evaluate how likely my segmentation is relative to the atlas. And the way it's typically done is I'm going to write product over all pixels, product over all labels, probability of that label at that pixel to the power of what your label assignment is. This assumes that your labels come from 0, 1. This is a cool trick that makes the algebra very easy and reading very hard. So paper writers love it. Because basically you read it and it sounds fancy, it looks fancy, and you can't for the life of you tell what's going on. So let's decipher this. And this is very standard formula that all of you should know. This is a very standard trick on how to turn your if statement with many classes into an algebraic formula that you can differentiate, right? So suppose my segmentation assigned 1 to the voxel, which means that I'm saying that it's inside. Then what I should do is I should evaluate the probability of that pixel being in the object under the atlas, right? So I'm going to take the probability of the object, right, the probability of the object, and raise it to 1. So that gives me the probability of that object. Should I be doing this L of x? Let's do that.